Hello, I'm Dr. Jeanette Stingone from the Department of Epidemiology here at Columbia University. This video is part of our machine learning series to serve as an introduction for public health scientists. So let's talk about some key concepts in machine learning. The first is data partitioning. Often in machine learning applications, we are trying to use patterns in the data to help us predict some outcome of interest. And while we're in this process of learning, right, we have the outcome of interest for our observations. So we can check if it's correct. And this is the purpose of, one of the purposes of data partitioning. It's to say we can learn these patterns that help us make predictions, and then we can test them, right? We can pretend we don't know the outcome for a portion of our data, and we can see how well we do in creating our prediction using that model we learned. So in data partitioning, we take our data set, as shown here on this slide, this is the first case, and we split it, partition it into what we call training and testing. You can see that training is often bigger than testing. A common split is 70-30, 75-25. You want to use the bulk of your data for learning your model, okay? Within training, we learn the patterns and we learn to try to predict this outcome of interest. In the testing set, we don't use that at all for learning. It's also called a holdout data set. We don't want to look at it at all. Once we have our model from the training set, we then apply it to the testing set, okay? Once we do that, we can obtain our predictions and compare to the truth. And we can get all kinds of evaluation metrics: accuracy, sensitivity, specificity. This is how we know, right, that what we learn in our data will apply when we don't know the outcome of interest, this unseen data. So this is one aspect of data partitioning, the ability to evaluate the models that we learn. The second piece, and I'm going to talk about this in more detail, is to avoid overfitting, right? Or to avoid only being able to make predictions in the data that we use to learn our model. And so for this, we'll often use something called cross-validation. You may have heard of this as k-fold cross-validation. The k-fold refers to how many different partitions you're making in the data. So as opposed to just generic data partitioning of training and testing, in cross-validation, we're taking our data set and we're randomly splitting it into k-folds. In this example, I'm using 5 folds. And we create these 5 folds, again, randomly, so that they look as similar to each other as possible. We train on 4, and we test on 1. And then we store those evaluation metrics. Then we do it again. But now, we switch the fold that we're testing on. So as before, we tested on 1 through 4. We trained on 1 through 4 and tested on 5. Now we're training on 1, 2, 3, and 5 and testing on 4. Again, storing our evaluation metrics and then doing it again. You can sort of see where this goes. We go through all of the different partitions. This allows us not only to assess how well we're doing, but it means that we're using all parts of the data for both training and testing. And that should hopefully help us create a model that works better in unseen data, which again is really the goal of a lot of machine learning applications. Another key concept are the algorithms, right? What are we using to learn these models? When we say algorithm, we're referring to the step-by-step procedures that we use to learn the final model, right? That mathematical representation of whatever it is we're trying to do. There are a lot of different algorithms, and they all have different strengths and weaknesses. So often the question we get is, how do I know which algorithm to use when? And like most questions in epidemiology, it depends. It really depends upon the goals of your research question. One, I think, helpful way to think about this is to think about each algorithm's ability to deal with interpretability and flexibility. This figure here is from the textbook Introduction to Statistical Learning in R, and it plots out different algorithms, not all, just some, in terms of their flexibility and interpretability. By flexibility, we mean how well does the algorithm handle complexities in data, right? How flexible is it? So you can imagine that regression-based approaches out of the box are less flexible because in order to get flexibility, you need to put in polynomial terms or interactions, right? So they can be flexible, but they're not automatically flexible. Whereas some more complex algorithms can handle really complex relationships within your data. The flip side of that is interpretability, right? How well are you able to understand why the model is making the decisions it's making? Okay, and so again, on that part, oftentimes the algorithms that are the least flexible are the most interpretable. Those that are the most flexible can be the least interpretable. Not always, but that's most of the time. And so really, I think what's helpful to think about is, what is my research question? What does it require? Flexibility, interpretability, a balance of both. And then think about which algorithms fit that. Another key concept is tuning. And this is very different than what we typically might do in a regular sort of epidemiologic or public health data analysis. So in tuning, we're referring to varying user-controlled hyperparameters to maximize model performance. A lot of these algorithms, they are data-driven, but they also have pieces of them, these hyperparameters, that we as users control. Okay, and so tuning is about looking over a wide range of values to find that value that maximizes our model performance. And so this is a key part of using these tools. On the slide here, I have the example from regularized regression. Regularized regression has this hyperparameter called lambda. Lambda controls the amount of shrinkage in this type of algorithm. So you have all of your coefficients from your regression model. This lambda controls how some of them may shrink to zero. It's a very basic description of regularization. The point here that I'm trying to get across, though, is that as you vary lambda, you can have more or less shrinkage. And you can see that here on this second figure. Here we have larger values of lambda. You can see that our coefficients are closer to zero. Here, when our lambda is very small, we have less shrinkage. And so our coefficients are just what they are. You want to find the point, right? And this is the purpose of tuning, where you're minimizing your error, but also keeping in mind that you want your model to be able to work in a new unseen data set. And so it's picking this value of the hyperparameter, that's called tuning, but making sure you're looking over a wide variety of space. So the last key concept I'm going to talk about is this idea of overfitting and the bias-variance tradeoff. In this context of machine learning, I'm talking about bias as the difference between our predictions that we generate and truth. Okay, so how close do we get for different observations between what I predict for an observation and what is their actual truth? For variance, I'm just going to simplify this a little bit, and what we're really talking about is how well my model will generate predictions in a new data set, right? How well it does. And so when I am talking about this idea of the bias-variance trade-off, I want for all of my observations in training to be as close as possible, right? Obviously, right? I want good predictions, but I don't want them to be so good that my model doesn't work well in a new data set. I want to balance this ability to represent what's in the training data, but make sure that it will also work in a new data set. So now let's go to this idea of overfitting. That means I'm learning so well in the training data, right, that I'm fitting really, really well to the training data, including its noise. We don't really want that, right? We want to represent these underlying relationships in our data, but we don't want them to be so specific to one data set. The idea of overfitting can be visualized on this picture here. So this is the extreme, where I have no bias at all. For every value of X, if you think of the blue dots are the observed and the red are the predictions, for every value of X, I am perfect at predicting the value of Y, right? But you can see that this function is not like a generalizable picture, right? You can see that I'm fitting to each and every little fluctuation in this relationship. And so we would say that this model has high variance. It's not going to do well in another data set that potentially has a different noise pattern. But if I looked at just the accuracy of my training data, it would look perfect, right? Because there's no bias. That's overfitting. The other extreme is underfitting, and that's what's on this second picture here. Now here, I'm doing a lousy job, right? For every value of X, I'm basically predicting the same value of Y. And so I'm not getting at any underlying relationships at all. But this type of model will behave the same way in any other data set. I'm certainly not fitting to noise. I'm not really fitting to anything. So this is sort of an extreme of underfitting. But underfitting is this idea that I'm not really getting the underlying relationships in the training data, as well as not fitting to any of the noise. What we want is this balance, okay? And that's this last picture here. We want to get a good representation of what is the underlying relationship, but not being so close in the training data that I'm fitting to noise. So you can see here, this is not perfect prediction. I'm going to have bias or difference between the blue dots, the observed, and the red prediction. But overall, I'm getting a better representation of the relationship between X and Y, which means that this model should perform better in unseen data or new data that has a different noise pattern. And so this is why we use a lot of the tools that we use in machine learning. The things I've talked about of the tuning of the hyperparameters, the use of cross-validation. All of that is to get us here to this idea of good balance between the bias within training, right? We're learning the patterns, using them to make predictions, but not fitting so closely that we start capturing noise. These are some of the key concepts in machine learning that I think will help you as you delve into the literature and learn more about this topic.